GPU memory spaces. GPUs have many memory spaces. All these memory spaces are not cached, so they depend on the GPU type. One important characteristic of discrete GPUs, that is the one attached through a PCI Express bus, is they do not provide virtual memory space. So the application data must fit in the device memory. So that can be sometimes an issue because, for instance, you have programmed your code for a GPU with 8 gigabytes and then you try to run it on a GPU with 4 gigabytes and it won't run. So that's an issue when you develop the code. Part of the memory spaces are divided between the work items. So this creates a constraint between the number of threads and the amount of memory available per thread. Let's look at that in more details. So you have the global memory. That's also what I call the device memory. And this is shared by everybody. Everybody can access every threads, every work items can access to this memory. This is a constant memory. This is a read-only one, or read-only memory. And for each work group, you have a local memory that is shared between the work items, and each work items has a private block of memory and some private registers. And all the registers are actually a big set of memory that are divided between, this big set of memory is divided between the work items of a work group. So the consequence is the more work items you have in a work group, the less registers are available to one work item. So the device memory, similar to the main memory, no virtual address space, highly pipelined. Read-only data, and usually it is cached. The local memory, it's a small scratchpad memory shared between the work item of a work group. It is fast and close to the processing unit, so the latency of access is small. But it's a small memory that is divided between the work items of a work group. So if threads are using too many of this memory, too many elements of this memory, then you cannot have many threads in a work group. The private memory is a set of blocks allocated to the unique work items. And you have the registers, and they are private to work items, and they are a subset of the big set of registers available to a work group. So the more threads you have, the less registers are available per thread in a work group. One important mechanism related to memory is what's called by Nvidia coalescing. The idea is, remember, you execute everything in a load step. So you have this is a memory access, this is a load to an address, and this is address prime, this is a load to address second, etc. So every work item is accessing a different address. And what the hardware does is, if these accesses are accessing different banks, the hardware can see that and see that it can do all these accesses in parallel to the memory banks. So that will be very efficient. So you only get one transaction to do all the accesses for the work items. The problem comes if, for instance, you are accessing B prime bit second, and they are all going to the same memory bank, not the same address, but all the same memory bank. In that case, you will get a serialization of the access, and that will slow down the program execution. So coalescing properties of the loads and stores of the work items memory accesses is actually an important property of GPU code. So the questions: what makes a GPU memory fast? What are the main elements? How are the number of registers available to work item related to the work groups? what is the influence of coalescing mechanism on the coding practice? It's a good idea to answer these questions to look at this tutorial that is on Piazza. See you in class.